Hello. Okay. Hello, everyone. It is my pleasure to introduce today's colloquium speaker, Professor Shayan Mookherjea from the University of California, San Diego. Professor Mookherjea received his PhD from Caltech in 2003 and has been at UCSD ever since. He's a recipient of numerous awards, including the NSF Career Award. His research is in design, fabrication, and testing of novel photonic devices for data communications, nonlinear optics, and quantum photonics. And today he's going to tell us about his work in integrated photonics.
Thank you very much. Thanks to Arka, who couldn't be here for the kind invitation. Thanks to all of you for coming. This is a weird angle. I'm going to try my best to look up more than I usually do. Most of us who teach classes are used to looking at the front row, because beyond that, the students are asleep. But here it's kind of the opposite. I've kept it very general. This is about integrated photonics. It's about the work we do. What you see here is a picture of a semiconductor wafer dating back to about 2008-9, where a group at IBM basically pioneered this work of designing photonic circuits on the same processes used for semiconductor manufacturing. And we were fortunate to partner with them on a small site on one of these things, trying to push the envelope of a particular type of device. So I'll talk about that one and others. The background here is that integrated photonics can be used, of course, to reduce the size, weight, and power, or the swap, of optical assemblies, and that's pretty much obvious. It's integrated optics. It looks very small, and it looks very light. Yes, it improves functionality, and as I'll show you examples, you sometimes can get really good levels of performance that way. I'll try to say something about what is the cost. This is a double-edged sword. Off camera, I would say something. On camera, I'm going to be a lot more guarded. And how long does it take to realize the concept? Whatever I say now, a funding manager could see the video and come back and complain. So I'll hum and haw through those parts. But I will show you what integrated optics can do, and I'll tell you how long it took us to get there. And of course, we are much better now and can do it a lot faster and a lot cheaper. So the answer to these questions basically depends on what it means to integrate optics. What is the optics that you wish to integrate? There is no general answer, so I'm going to present 4 examples from my group, one from the area of linear optics, one from the area of electro-optics or electrical signals, modulating light, one from the area of nonlinear optics, and then the hot topic nowadays, quantum optics. 1 examples of each. Now today, if you have anything to do with photonics or integrated optics, it seems the only photonics today is about datacom, data communications. Examples here of chips that are mostly VLSI, CMOS, and have some optics on them date back more than 10 years ago, where the optics was flip chip mounted on top of these now commercial transceivers. There are recent versions of them now, startup companies. This is, of course, 3.5. It is sort of VLSI photonics. Intel's involved. I know Microsoft has interests. This cartoon picture here, which is actually quite old, shows you where the optics comes into this. There's basically a laser die that is in some way attached, die-mounted, usually flip upside down on top of waveguides. And this technology has been with us for a while, and it really, you'd be forgiven for thinking this is all that there is. There's certainly a lot of jobs here. But it wasn't always the case. Not that long ago, integrated optics was more than just datacom. Here are examples from a book called Optical Integrated Circuits, published in 1987, showing an integrated optical circuit in lithium niobate using acoustic waves and transducers to build an RF spectrum analyzer or to build an optical CD disc pickup mechanism. There are many, many examples of this where there are multiple things going on. There's some nonlinear optics, some electro-optics, focusing of light. There's a laser diode that's attached to these waveguide systems, and even detectors. And the point here is that in the future, it's not going to be about datacom alone. Industry is doing a great job with datacom right now. Just some examples of where we need optics, whether it's in sensing, diagnostics, whether it's in ranging and position, VR displays, the bandwidths needed. It's very hard to find an oscilloscope, and has been very hard to find an oscilloscope with more than 50 gigahertz of analog bandwidth for several decades now. And maybe optics can help. In precision metrology, whether in reading out an AFM cantilever, optics now has a role to play. People are working towards integrating the optics on that AFM head. Certainly in quantum information processing, optical interconnects in and out of a cryostat. That's something where we think integrated optics is going to play a role. Perhaps in computing, we don't know. There's an explosion of interest in free space, actual space, like these microsatellites. You just don't have enough power to put conventional lasers in there. And you don't need that much distance. It's 1/r losses to a couple of 100 kilometers. Integrated optical chipsets are very, very attractive. Of course, the challenges are how do you acquire the beam? You need apertures and all of that. So there's a lot of stuff to be done here. But there are certain common threads of what we need through all of these functionalities. And again, I'm going to pick one example from our work of, I'll start with the linear optics example. I will say that our goal as a university research group was improve performance. The swap reduction, yes, it will happen, and industry will do a better job than us. So for optical filters, the benchmark for us was not what are the optical filters that have already been made. It's what can you do with DSP. And what you can do with DSP, basically FIR filters, and you can make analog implementations of this. Basically, you will get a few dB passband insertion loss if you get about 80 or 90 dB stop band rejection. This is not super hard, but these are typically audio to a few hundred megahertz frequencies. And the question is, can you get this level of performance in the optical domain? Could you get a few dB of insertion loss, it's a bandpass filter, with about 90 or 100 dB of on-off contrast? And that makes the optical problem quite interesting and difficult. DSP gets very hard once you ask for filters extending out to gigahertz. It's just simply too many taps and too many bits being processed. Whereas for optics, 10 gigahertz or 100 gigahertz is quite easy to actually send through and process. The building block is something many of you are familiar with, a microring optical filter. It's a single pole resonator. There's an input waveguide, there's a through waveguide, there's a drop port. Here's the add port if you were to use it. This particular example, you can't see the optical waveguide. That's sort of intentional. I'm trying to show integrated optical examples. There's a micro heater on top of it. This serpentine metallic pathway is just a small heater that tunes the resonance frequency of the ring. This is popular. I mean, the cartoon of the microring, you can see it in a Bell Labs paper by Marchettini in the 1960s. It's been known as the thing you want for sensors, for add-drop filters, and it has this single pole drop. Here's where you get at the drop port. One of the wavelengths gets picked out, and there's a notch or a critical coupling now in the through port. The problem, if there is one, is that the extinction that you're seeing, this is a theory calculation, you can rarely get it this precise. The extinction is about 10 to 20 dB, and that's not really good enough for anything other than data communications. And so microring optical filters have predominantly been used in WDM, or wavelength division multiplex systems. The question is, can you do better? And just like the digital signal processing people, well, if you can make multi-order filters, you can probably do better. And so like others, we did. This is an example from our work. This is a 5th order filter. What you need to do here is to get the gaps in the lens kind of accurate, because the coupling coefficients are not uniform. Just as in a digital filter, you don't have the same coefficient. Here, you have to get the coupling coefficients right. Plenty of theory out there by now, whether you want a Bessel filter or a Butterworth filter and how close you can get. The fundamental reason for doing this is to break this trade-off between the contrast, on-off contrast, that is pass-band, stop-band contrast, and bandwidth. And if you have a single pole filter, you can work out the math. I'm going to skip the math here. Basically, the single pole filters, if you have a wide bandwidth, given a certain free spectral range, you're not going to get a lot of contrast. And these were actual measurements showing that you could get a 4 nanometer bandwidth, enough for superchannel or a thermally insensitive passband, and still get 60 dB contrast. This has been known for a while. Before us, there was Brent Little's research and company, Little Optics, showing that for a first-order filter, you simply don't get enough contrast, or you get some contrast, but you may like to get more. But if you can go to a third order, and these are measurements, and by the way, an 11th order, you get much more contrast. But these are glass filters. So what does that mean? It's difficult to get a large free spectral range, or reasonably large even by our standards today. This is normalized bandwidth, normalized to a pretty small free spectral range. It's because the bending radius for the microrings is quite large. That makes the free spectral range quite small. Today we are used to 100 gigahertz spacings. Soon we're going to need 400 gigahertz spacings, and it's difficult to do that with glass. Glass is not a semiconductor. You can't tune it very fast. You can heat it, but it's not a good conductor of heat either. So tuning these things is extremely slow. And these were designed as the whole filter moves around. So you really can't control the individual poles and zeros. With silicon, our work showed basically that you can get very high contrast. This is an actual measurement of a 100 dB on-off contrast. These are two 5-ring sections. It's still challenging to get this kind of a measurement on a single chip. 100 dB is 10 to the minus 10, so any amount of stray light going through from input to output port, even the two ports looking at each other through the substrate, certainly makes 100 dB quite hard to achieve. But you can sort of get around some of the problems by using two chips. Other groups, Mike Hochberg's group, among others, have worked in this area too, and we're all sort of getting to the 100 dB single chip goals. The size is, of course, extremely small. These are microchips, so that's not the issue. The swap comes for free. But the performance is quite good. Once you get the filter coefficients right, the passband is flat. The group delay ripple is actually quite good. And the overall insertion loss of the two sections was about 2.8 dB. So it's certainly possible to make high-performance optical filters. So why don't we use them in all our systems? Because these were the best performing chips, and there were very few of them. It's still hard to get the yields very high. So in terms of cost and time, this took several years to get to. And we still can't routinely get this in every fab run. It's certainly possible to lithographically make very long couple resonator waveguides. And so we have made, this was the work with IBM, 235 couple ring resonators. And as our paper will show, light propagates through this. You can see stop bands and pass bands. This is not just some amplified spontaneous emission going through it. It's coherent light. Light preserves coherence going through the sequence. And the way this thing works, no light is going to go through unless the ring resonances are close enough to each other within the locking bandwidth, essentially. And so to get 235 to work, it means that something is right about the fabrication. This is all passive. There are no PN junctions across the rings. Here we had fewer, about 50 microrings with PN junctions across each one. In fact, 2 PN junctions on each microring. So now you can electronically move this thing around. But the trend is not towards these very, very large sequences. Not only is the fabrication sort of difficult, and they're useful in certain specific cases, but you can get 50 dB contrast even with a fifth order filter. And so the point now is to try to do something with those filters. Here is a nonlinear microring that will convert 2 wavelengths into a third wavelength, but it's followed by a tunable fifth order filter. So you can pick out the converted. And I'll show you examples of this thing working a little bit later. So we have a 100 dB filter. We can put PN junctions on these very long cascaded sequences. What's next? Really, the first thing that's next is filters plus other things. And so one of the things being measured in my lab right now is where there's a microring in here. There's a fifth order filter before it. There are 2 fifth order filters after it. This is a WDMD mux. This is an ASE filter or an amplified spontaneous emission filter. There are different outputs here. You can barely see them. And they do work. We've cut this chip up to measure the individual pieces. The good news is that we can now put down filters in different parts and have them electronically controlled. And there's a reasonable chance that integrated optical filters are truly integrated. The filter is not just the thing. The filter comes with other stuff that we've integrated. We are close to DSP-like performance, tantalizingly close. What I mean is this 80, 90 dB of contrast and a few dB of insertion loss. However, that's not fiber-to-fiber insertion loss. Once we add in the fiber insertion losses, definitely there's a hit. Very good fiber couplers tend to have about 1 dB insertion loss, but that's the whole project in itself, making very good fiber couplers. Making very good fiber couplers together with this kind of stuff, that's still an open challenge. So typically we'd see 6, 7, 8 dB end-to-end insertion loss, and that's frankly not that great. If you need 100 dB contrast today, 7 dB insertion loss is not bad. You would probably pay for that. But we can do better. Also, these are polarization dependent. Silicon waveguides tend to be TE guiding or TM guiding, typically not both. If you have low PDL, can you make a microring that's sort of robust to fabrication? Or does it randomly go from TE to TM and mess up your transmission spectrum? So there's something called polarization diversity in that you make 2 circuits for the price of 1 and hopefully balance your responses, but that takes time and effort and some fabrication. And finally, of course, the point of living in silicon is to integrate the driver and stabilization electronics. And like many optics groups, we sort of throw this over the fence and say, come on, 80% of my department are electrical engineers who make circuits. Surely someone in there can make me a circuit. But people in optics have been saying this since the 1960s without much progress. The circuits people make circuits for themselves, not for optics people who have sort of handed a problem to them. But maybe the attraction of having a truly 100 dB filter will bring them out. So that is the linear optics example of where it took us about 4 or 5 years with this goal in mind, DSP-like optical filtering performance. And it's actually a fairly good success story in that we are getting there and we are confident enough to put the filters with other stuff on a fab run and hope to make them work. More experimental stuff. In some sense, more traditional stuff. The Mach-Zehnder modulator goes back almost 100 years. But in electro-optics, it certainly goes back also to the 60s. Basically, 2 arms, introduce phase shift in 1 arm and then recombine. In silicon photonics, which some of you know, you can certainly make Mach-Zehnder modulators. They're fairly long, several millimeters. And here's the cross-section from Mike Hochberg's work. It's a fairly complicated process. We have come to accept this as the standard. This is how you do it. You have a waveguide in the middle. You dope P and N. And then you have P plus on one side, N plus on the other, even more doped P and N. Then you silicide, right there. Then you add metal. You move the metal away from the waveguide core to reduce the propagation losses. So you typically may need 2 levels of metal. And so you need a number of mask layers. And this is not something you would walk into any university clean room and try. Some do, but mostly you go to a foundry. And so that you have to reduce the risk on your design and wait a while, and the cost goes up. At the end of it, you get a modulator that typically has about 30 gigahertz bandwidth. And it's been like that for about a decade or so. The low V-pi-L is a benefit. It means you can drive them. If your length is long enough, you can lower the drive voltage. So if you look at an arbitrary waveform generator, that typically has a 1 volt swing, peak to peak swing, 800 millivolts. And so the traditional lithium niobate modulators, where you needed 5 volts, you can't just drive them with CMOS electronics, whereas these things you can. And so inside most modern transceivers are these kinds of modulators, and for today, 10, 20, 30 gigahertz, 50 gigabit per second is enough. But that technology is evolving every 2 or 3 years, and so this is not going to be the last word. So our goal was, well, we know lithium niobate is this gold standard of electro-optic modulators. Photonics has gone silicon photonics. Can we bring the 2 things together? So a few years ago, we were looking at how to integrate lithium niobate with silicon photonics. What you see here is a foundry fabricated silicon photonics die, just waveguides and splitters and combiners and rings and that kind of stuff. Lots of waveguides, I think about 110 different simple optical circuits, left to right. On top of that is bonded lithium niobate, thin film lithium niobate with a handle. So what this is basically make a wafer of silicon photonic components. In cross-section, here's the silicon waveguide. It has a certain width. And then this is the bonding surface for thin film lithium niobate, top-down. And it's a fairly strong bond. Once we're bonded, we remove the handle, do other stuff with it, even make electrodes. I'll show you in a second. And so there are outgassing channels here. What you're looking from the top Outside, there are these silicon photonic directional couplers. Then it goes underneath, and it's out of focus here. You can't see it. So lithium niobate is bonded over that region. We have bonded lithium niobate to silicon circuits. We have bonded lithium niobate to silicon nitride circuits. And these are large areas, 2 by 2 centimeters. These are not microplatelets that were shards of lithium niobate. We've also done BCB-assisted bonding. This is essentially oxide bonding. We've done layer transfer. Looking through a microscope, what you basically see, I hope this is in focus, you can see lots of these waveguides coming in pure silicon photonics with an oxide cladding. And then it transitions underneath here. Now, silicon is the highest refractive index. So what this means is that the light remains in the silicon waveguide if it's wide enough, if N effective is high enough, as it goes underneath this edge. And then, as this showed, the width of this feature can change. It actually changes from about 650 nanometers down to 320. What this does is lower the effective index and pushes the mode into the lithium niobate, which has the next higher index. And so, even though at this edge looks fairly rough, the light, as it goes underneath this, remains in silicon, and that's a pristine waveguide, foundry fabrication. Somewhere in here, we have a taper that tapers down the silicon, nothing in lithium niobate, and it pulls the light into lithium niobate. And so by lithography in silicon alone, we can bring the light into lithium niobate and bring it back down out of lithium niobate. And so, of course, we showed a bunch of passive devices. We can have bends in silicon. We can make light zigzag underneath lithium niobate. All that's fun, but the real goal here essentially is whether we can get a modulator. And so then you remove the handle, you remove the stuff that you don't need, and you actually put down ground signal, ground electrodes. So again, the input here is in silicon. This is the kind of mode. It transitions into the bonded region but remains in silicon. That's the highest refractive index. Then the silicon tapers. Now the light gets pushed into lithium niobate. It looks faint, but it's on the same color map. 87%, I think, of the light is on lithium niobate. And so now it's very close to a conventional lithium niobate modulator, except with a smaller mode. And now you can match the RF indices and the optical indices by using lithography in silicon alone. So the lithium niobate never has to be etched. And etching lithium niobate is not only difficult, but it induces charges and degradation, and it drifts with time. This is just essentially pasting some lithium niobate on top of a silicon photonic circuit, getting the indices just right. And I encourage you to look at the paper in the abstract. The modulator has a 3 dB electrical bandwidth exceeding 100 gigahertz. So it really gives us some extra knobs to play with, and it gives us a modulator that outperforms the state-of-the-art quite handily. More details in there. What's next for modulators? Well, certainly RF photonics. There's been this goal of increasing the bandwidth from the lithium niobate modulators you can buy, 10, 30, 40 gigahertz to something much broader. We think we can do that. VPIL hasn't gone up. It's about 6.5 volt centimeter. Certainly, as you can see from the list of authors, there are a lot of people contributing to this. Gabe Rubiz's group is in RF. Tony Lentine leads the foundry at Sandia. And new processes had to come up, a number of students. So the dollars here are sort of conservative. They multiply certain large numbers. But we can certainly make different circuits on the chip side by side. We can have multiple modulators fairly easily. Again, no lithography in lithium niobate. One bonding step and you're done. We can make linearized modulators where you have multi-sections in series. The harder stuff is, of course, the more exciting things. It's in a silicon platform now. Lithium niobate has come to silicon photonics, so we should be able to integrate bias controller circuitry and maybe even detectors. So the whole thing is just one little package. And certainly now there are SiGe CMOS drivers within the last year that have a DC to 95 gigahertz bandwidth. So the timing on the SiGe side is also very good for integrating with an optical modulator that has that much bandwidth. Previously, we were limited to about 30 gigahertz. And to some extent, eventually this is going to find its way into the datacom industry as well. Should there be need for single channel NRZ, plain vanilla format modulators with 100 gigabit per second from a single laser? We have the modulator, the laser certainly exists, the detectors are now the challenge. Can you get 100 gigahertz bandwidth out of a detector? Only InGaAs is the known technology to do that. That brings yet another material into the flow. So once we can get germanium detectors or something, CMOS compatible to 100 gig, it'll be quite interesting. All right, on with our sort of abbreviated whistle-stop tour. I want to keep some time for the quantum stuff. I'll be brief on the nonlinear optics here. Just one example. It's always bothered me how easy it is to buy a mixer in the RF domain. You buy a mixer, and you have two inputs, and you get the mixing products, buy a filter, and you get the new frequency that you want. Your cell phone does it digitally. There were analog things with knobs in the front that you dialed. And it really costs a few dollars, and an optical version of that is something in a black box, typically in nonlinear mixers, cost $50,000, big lasers. Mode matching is a problem, things drift, there are too many knobs. But this sequence can be done on a chip, and it can be done at low power. And we were interested not at the 5-watt, 10-watt regime, because you have this technology, but what can you do with a milliwatt of pump power? Can you actually wavelength convert? The first kind of mixer we looked at is obviously just a waveguide. This is a spiral waveguide with PN junctions across it to reduce the loss. As you reverse bias the PN junction, you can get about 15% conversion efficiency, which, by the way, is quite good. We're already talking about percentages, not minus 30 or minus 40 dB. You can get this with about 100 and something, about 150, 160 milliwatts of pump power. But we can do better if we're willing to sacrifice the broadband. If we use a microring, here is a microring whose radius is 20 microns. What does 20 microns mean? What can you do in 20 microns? Well, in 20 microns, you can detect. You can have a sensor pixel. In 20 microns, you can have a micromirror, switch. Or in 20 microns, you can roughly have a spatial light modulator pixel. Now, in 20 microns, you can shift your signal by about 30 or 40 nanometers with a conversion efficiency of what looks like minus 12-ish dB. But that's good news because the detector sensitivities are typically minus 16. The pump power needed is now on the order of a couple of milliwatts. So in 20 microns, you can wavelength convert with enough headroom to detect, and maybe even insert a filter in there. But you only need a few milliwatts of pump power, or a telecom level pump power to do this. And that's quite exciting because these have all gone to array technology. We want to take this into an array technology as well. And so, is there headroom for a filter? So here are the nonlinear mixers, and they're followed by a filter. What does this mean? It means if you have, for instance, here's an example of a non-best case, where here's the input, here's the pump, and the mixing gives you that tone, and you want to see that tone. In integrated optics, if you were to stick a detector, the detector would be blinded by this and then by that. So what you need now is a filter that knocks down this, that knocks down the residual input, unused pump and residual input, and isolates the desired tone. Can you build such a filter? Yes, you can. And so the filter knocks down the pump by 50 dB, knocks down the signal. We didn't get 50 dB here, we got 44. And this, there was some insertion loss, about 2.5 dB. We'd like to make this a little bit lower. So it is entirely possible now to create nonlinear mixers with a few watts of pump power, followed by a filter that isolates the tone that you want. Obviously, the next step, add in the detector and make this a seeking receiver. So then what can we do for quantum? Well, that's an even bigger challenge in some sense, because it's, to me, really not clear what photonic integration for quantum does. I'm just going to focus on quantum communication, where there are circuits now for sources, for detectors, and for the stuff in the middle that I'll just call circuits. And so these are all looking fairly involved because they're multi-sectional circuits. And these especially look like they have lots of control knobs. And the detectors are often, well, the silicon ones, you can put silicon circuitry right next to it. This is a commercial technology. You get arrays of single photon detectors, whether in silicon or I think in 3.5 now. we are now seeing arrays of SNSPDs, or superconducting nanowire single photon detectors, and that's very exciting. Though some of the fabrication techniques are a bit serial. But we are soon going to see arrays of these SNSPDs that you can read out. On the material side, though, there is a problem. And I know many of you work in the area of quantum. This is a list of materials used recently, and I mean within the last few years, in quantum optics. And simply, this is multiplying. I mean, every time I look at it, people are bringing more and more materials into this. And so from the point of view of photonic integration or integrated optics, it's very difficult to create a process or even an understanding of what a process should be. So we don't try. We look at it from the other viewpoint. What do you need for instance, for quantum communication? There are two sort of big problems out there. There's a quantum key distribution problem and a transceiver problem. What I mean by quantum key distribution is basically, let's see, two cartoon characters decide they want to share an image of an airfield for whatever the reason, and another cartoon character is in the middle, and basically you want to make sure that she only sees this kind of image, whereas Alice and Bob see the correct image. And the transceiver for a quantum state is basically you don't have deterministic amplification for quantum states, and therefore you need to build something called a repeater that can extend the reach. So you exchange entanglement between these intermediate states, and thereby the two ends of the network have now established entanglement between them. And you can try to do quantum teleportation on a photonic chip. Circuit-wise, it's not super hard. It's a bunch of beam splitters and phase shifters. The technology is very, is actually tantalizingly close, but some of the functionality is quite difficult. You need, very efficient sources. You need to get past post-selection and a few other things. Let me mostly talk about the simpler problem, the one that's closer to application. I'll say a couple of things about transceivers at the end. For QKD, the idea basically is that Alice has a message. A message is a sequence of bits. And she also generates, and here's where the quantum stuff comes in later, but even algorithmically generates a key. The key is XORed with Alice's message. And then you get an encrypted message. This is that bunch of bits that you see over here. It's encrypted. So detecting that has very close to zero mutual information with the original image. And then if you have the key, you can XOR it back and get that message. The problem, and this is very exciting, there are big headline results about this. The problem is that it requires lots of resources. And a lot of optical interconnects, a lot of photonic integration today is about reducing this number. How many picojoules per bit or picojoules per bit per millimeter do you take to communicate your data? And what QKD does is basically because of this XORing and the key of the same length as that, this one-time pad idea is just 100% increase in the number of bits that are handled by the network. And so in a field in which 10% and 5% improvements define the state of the art, adopting something like this just sets you back by a factor of 2. And so this is probably going to be difficult for adoption, widespread. QKD has been around for a while, and it sounds very exciting. And I'm sorry if this disappoints some of you who are looking forward to, QKD as the first real quantum application. I really don't think it's going to happen. It's just too costly, and cost is dominating everything. However, ubiquitous QKD, I mean, the word will definitely get used. Business people will make sure of that. But it's probably not going to be one-time pads of messages. It may be QKD of routes. The thing that you may want to authenticate is not the message of the airfield, but the routing table. That is updated every few milliseconds or at even longer intervals. So maybe authenticate routes, not bits. That's one way out of the, that's sort of not solving the problem, but solves a different problem. The other thing, and maybe in parallel, is that you really have to integrate this with the transceivers. And what a transceiver looks like, if you take it apart, is basically the optical fiber plugs in there. So that's about yay big. And the rest, there's a lot of empty space. The photonic chip, by the way, is that big. This is not our work. This is Luxtera's transceiver. Just to give you a sense of the scale for what it is, where is the optics that generates 100 gigabits per second? Well, it's that small. And so where does QKD fit into this? Well, what you can get for QKD, what is state-of-the-art QKD, is basically not that small, but banana-sized, essentially, right? This is the hardware that you get for QKD, and we would like to sort of take that and bring it into the desirable form factors that you can just make pluggable. So on this trajectory, we started about 2011, 2012. We moved to silicon to show that you can get reasonably good quality photon pairs. I'm saying reasonably good quality based on our knowledge today. Back then, it was very good quality. We showed you can do WDM, you can control the degree of entanglement, that you can do temperature stabilization, that you can reduce the pump powers to microwatts. Some of the nice results, this is a microring resonator that has a PN junction across it. What the PN junction does is basically there's a weak photoconductivity, whether it's surface states or TPA or some defect states, we don't know. But when the pump light is resonant with the microring, we get a reverse biased photocurrent of a few microamps. And that's crucial. Few microamps is detectable with relatively cheap electronics. Nanoamps would not be detectable, and milliamps would deplete the pump. So we have to you basically have to design this PN junction so that it's an active microring with a Q that's close to 1 million. And then you can actually use this PN junction readout. Another thing, in many labs, people use mode lock lasers for generating pairs. And simply, you can't put a mode lock laser inside a transceiver, and it's way too expensive. If you're using a mode lock laser, you can afford to buy a nonlinear crystal. You don't need to use a microchip. And so we wanted to get away from this mode lock laser. So here's an RF sine wave oscillator, just an RF oscillator. And it drives a diode, but it's a special diode. It's a nonlinear diode. It's a step recovery diode. What this does is basically at the same rep rate carves pulses of about 70 picoseconds into the optical waveform. This is going through a modulator. So it's a modulator driver based off an RF sine wave and a CW laser diode and an electronic diode. And this 70 picosecond matches the cavity lifetime of the microring with a Q of about 1 million. And so now you have a pump whose width matches the cavity lifetime. What that means is when you look at the joint spectral intensity of the signal idler photon, you get something very close to a circle. It's not a perfect circle. If you have $1 million and a breadboard, you can do better than this. But the SVD shows one dominant eigenvalue, and this is typically what you want. When you want to do QKD or other quantum applications, you want as close to a pure state as possible. We are working on eliminating these, but for QKD, at least that's fine. So we can get a reasonably good JSI by carving pump pulses using relatively cheap electronics and CW RF and CW laser diodes. How about the microring itself? Could we get better performance out of that? I think so. Very recently, we sort of pushed the performance of the microring. So now we can get cars of 12,000. We have a paper now with 19,000. The G2s are actually quite low. Even at a megahertz, it's less than 0.01, which is actually quite good for silicon. The spectral brightness is extremely good. We have a comparison table in there, mostly to show how quickly the field has evolved. The first silicon structure sort of came up about 5 years ago. Now we would argue that a properly designed silicon microring would be the thing that you would use to generate pairs at 1550, maybe at 1310 as well. We have a paper recently showing that a properly designed microring can generate pairs either at 1310 or at 1550, in fact, both simultaneously. If you were asked to design a lithium niobate or a nonlinear crystal that generates entanglement at 2 wavelengths simultaneously, that's a very complicated polling pattern. And here you don't have to do that. There's a different approach to doing it, and you can get reasonably good visibilities, not record visibilities. But you do get resonances at both wavelengths, and you do get resonances. You do get transient visibilities in the high 90s using a simple microring. And since it's a wafer integrable technology, by working with companies such as Intel, who have integrated the 3.5 laser on board, we can now actually pump these with a silicon hybrid laser. That's a 3.5 bonded to silicon. And even in this case, the car was several hundred. G2s were quite low. And so you don't even need the desktop laser. You don't need the laser instrument. there are still power dissipation issues here. Where does the excess power go? I'm not saying this is the uniform solution for everybody, and it's certainly extremely costly to do this. But the technology is there. Should you want a one-chip solution without any external light sources for generating photons, I don't think we're that far. I will make an observation, though. Typically, and this is not something often said in the quantum community, the pump lasers in the order of tens to hundreds of milliwatts, at least in the past. Now we can use microwatts. That's an improvement. But typically 10 to the 18 or 10 to the 17 photons per second are used at the pump. And at the end of the story, when you're detecting something, whether bouncing off a satellite in space or something, or even at the other end of the lab, you end up with 100 to a few thousand photons per second of useful information. There is no practical deployed communication technology other than deep space communications that lives with this level of efficiency or inefficiency. This is about minus 160 dB. And so it's a severe barrier to adoption as a practical UWEE technology. And then it costs a lot on top of that. And so the efficiency of this as a communication platform, as an interconnect platform for quantum, is certainly something we have to overcome. We have clawed back 6 or 7 orders of magnitude, but we have a long way to go. We are part of this NSF national program called Acquire that I think IME and ARC are also part of. There are people here and at several other universities. We are basically trying to overcome some of these engineering challenges. So what's next for photon pair generation? Well, a lot of different things. I think a silicon photonic QKD transmitter is imminent. We'll probably have it within a few months. The laser integration is certainly possible. We did a proof of concept, but it's a fantastically expensive process and sort of held by a few people. So it's possible if you want to pay for it. Brighter or on-demand photon sources. Well, we have pushed silicon as far as we can, I think. Qs of 1 million being repeatedly made. Yes, you can get one-off results slightly higher. We have done oxidation of the sidewalls. We have done atomic force microscopy-based sculpting of silicon circuits. We've tried a lot of crazy stuff. You can see our papers. But I do believe that a new approach is needed, perhaps based on lithium niobate, now that we can bond that. And use circuits. So that's a sort of a development project, and we're sort of excited to start that now. On the silicon side, yes, once again, it's time to integrate simple circuits. And that's a common thread through all of these. The filters need it, the nonlinear mixers need it, the modulator needs a bias control circuit, and even the pair generation circuits. And that's still been something not very easy if you wanted to bring an integrated circuit onto a photonic chip. Most people don't know, including us, don't know exactly how to do it. But if you want to buy an integrated controller for your tabletop experiment, you just go online, do a Google search, and maybe even buy it off eBay. That gap has to close, we hope. We are looking at some integrated optics for single photon detectors. Single photon detectors have certainly reached a very good level of performance, exquisitely low timing jitter. But the collection is a challenge. And hopefully we can improve certain things there using integrated optics. And the Acquire program is actually about quantum repeaters. And really, it's just getting started. All the groups are trying different ideas, from atomic systems to diamond to quantum dots. We're just trying different things to see which one will work. So I think I'm almost out of time. With that, I'd like to thank you all for listening, thank our sponsors, both from the government, from industry, our students. If you do get the time to come to San Diego, it's always a good thing. Please do come and visit us. I'll be glad to host any of you. Thank you.
Do you have any questions? Okay, I have a question. So in the superconducting circuits community, there's a lot of interest in high data output and energy efficient electro-optic modulators. Can you use your lithium niobate Mach-Zehnder interferometers for those?
We hope so. The problem right now with our modulators is that they've been designed for data communications. And so the drive voltage that you need is designed for data drivers. And so there's typically a V-pi-L product. So we'd have to design it for the output of the superconducting circuits, which is typically much lower voltage. But there isn't a fundamental problem towards trying those. Yeah.
Okay, if you have more questions, we have time, so please come down here. And in the meantime, we'll thank the speaker once again.
Thank you.